Welcome back. My name is Jesse. I am a tutor in Melbourne and I also make GAMSAT videos as well. So in this video, we're going to do another sample section 3 walkthrough video. It's going to get me every single time. It's 8 questions. These are actually slightly easier than some of the other ones that I've written. I'm trying to actually jumble them up a little bit in terms of difficulty level. And you might have seen on the resources page, I've also now updated the table so it now shows a difficulty rating from easy to medium to difficult to very hard to impossible, I think I said, or something insane or something like that for like really difficult ones, just so that people can get a better sense of what to expect. Because I know when I was going through my practice, there's a lot of talk of the green book from ACE being a little bit easier, a little bit more content-based, and book 3, the pink one, being a lot more reflective of it, and that the questions are a little bit more challenging than usual. And then obviously every sitting people are making complaints about different questions, saying it's getting trickier and trickier. So I think having a good gauge on like what is easy, what is difficult in relation to ACE material is probably a good thing to do. Again, this is just my kind of rating of my own experience, where I would kind of put it in terms of the depth of thinking that you have to use, the amount of reasoning or deductive skills that you need to use as well as that just in terms of how much content it might be relying on, or the speed at which you have to kind of process information and say do calculations or think in a kind of relational sense. That kind of puts it higher and higher up the hierarchy. So we've been doing a lot of kind of medium to difficult level questions. I did want to start with some tricky ones to get people really kind of challenged, but what we're going to do today is go through some that I would put on the easier ranking. You'll find that they are a little bit closer to a uni exam, although still it's not going to be assessing your memorization of facts or anything. Anything that's specific or technical you'll be given in the prompt, and I'll point that out as we go through it as well. There's just a handful of small scientific principles or principles from first year biology, chemistry, or physics. We're going to be looking mostly at bio today, that might be assessed or called upon. So this kind of really helps demonstrate what we mean when we're talking about it not being a theory exam, but at the same time being able to reason and understand the theory still being key to being able to do it. So that's part of why the crash course series that I did for chemistry and physics happened, because I want to make sure that people who are coming from a non-science background are up to speed with the key principles that they may need that may be assumed knowledge, but remember that they're not going to assess it from a technical standpoint. They're going to expect that you're going to layer that into your reasoning to rule questions or answers in and out each time. Another disclaimer as well, obviously these are all my own questions. These are not ACE material. They're modeled to try and reflect the ACE material. Where I can, I try to have the information be scientifically correct as well. I usually background research all of these, base them often off real empirical research as well whenever there's data and things like that. Every now and then though, I may actually alter things that may not be taking into consideration every scientific principle in order to actually develop a line of reasoning in the question. So if for any reason you were to do your research or you to know something outside of this that says, oh, actually that might be wrong, ignore that, go with only the information that's presented to you. Anything that is beyond first year biology or chemistry or year 12 physics is not required to reason the question. So again, don't come into it with any preconceived idea of how you should be reasoning it. Stick with the information that's given and then you'll be fine. The other thing is, we know science is complex. It's horribly difficult to write questions that don't have any conflict when really there's all kinds of stuff that I'm not aware of, like with much more technical research into organic chemistry and this and that I have no idea what's going on with. And so I'm trying to keep it as accurate as possible, but don't take it as gospel, basically. It's there purely for the practice. The reasoning still works. I've tested all the reasoning in the questions, which also brings me to the point of some people have called out in the comments a few errors in some of the questions, which I appreciate. So thank you for going through that and taking the time to leave a comment and letting me know. I do try to pump these out quite quickly, but I think I'll try to put them through a little bit more of an editing process to make sure there's fewer errors that need to be changed. But I'll also be going back through and updating the past videos. I'll probably keep the originals up as well, but I'll be re-uploading new versions of ones that had a number of errors in the questions, so that there's no confusions or anything, and so that people aren't being led down the wrong path. They're just small things, but I'm a bit of a perfectionist with any of the work that I actually do. It's a bit of a cliche, I guess, but I'd like to have this as being as high quality as possible, regardless of the fact that it's a free resource. It should be to a high standard. So if you do notice any errors in the reasoning or in the answers, still just let me know in the comments, because it's good because I can just pin the comments so that everyone else can see it in the interim, and then I'll do a re-upload as well and fix any errors. I always go back and change the resources page immediately if there's any typos or anything like that. But the actual videos themselves, they obviously take a little bit more time, so I'm working on getting that done as well. All right, let's just dive right into this one. So this is a lot of biology, a little bit of chemistry as well, but mostly biology and looking at cell signaling. I've decided on this one as well to have the same number of questions. There's 8 questions in this set, but actually have both the units go over effectively the same principles so that you can develop your understanding of it as you go, to see if that helps with your ability to answer the questions as well. So that it's split into 2 units, but it's all looking at blood pressure regulation and the angiotensin kind of pathway. So note again, even though it's in first year biology, this is an example of something where you wouldn't actually need to know anything specifically about that hormonal pathway. It'll all be given in the question, which is what we'll look at. So if we look here, Unit 1, corticosteroids are a class of hormone produced by the adrenal glands and which have a number of functions within the body. Aldosterone is a subclass of corticosteroids called mineralocorticosteroids. Hope I'm saying that right. Hey, look, there's a typo. I'll have to fix that. Small little things, right? Like this is not going to, obviously, we know what that is, but look, ACER don't make typos, good on them. I'm going to try and do the same. So then a 21 carbon containing compound, which is synthesized from corticosterone via aldosterone synthase. So a lot of the time, whenever they're describing chemical reactions and there's a picture, there's a diagram of it, they're often just putting into words what is in the picture. So whenever I see that happening, I usually start skipping at that point. But you can see, for example, it's mentioned a 21 carbon containing compound for aldosterone. I'm assuming that may be helpful in case it gets into any stoichiometry or anything like that. That's the only thing I'd really be taking from that paragraph. Otherwise, this to me, I prefer visuals. This makes way more sense to me, and I can probably pull information from that way faster than I could from the sentence. Aldosterone acts to increase sodium reabsorption. So I've got now the function in the bloodstream at the kidneys to regulate blood pressure and blood volume. So all that's connected. And then these mineralocorticosteroid receptor antagonists, or MRAs. So we get that definition coming in now. So I'm just going to make note of that. Anything that I'm underlining, obviously you can't underline in the real exam. Underlining for me here is just to kind of point out these are the things that I'd at least be making a mental note of, or else scribbling down on the scratch paper as well. So these MRAs antagonists are an inhibitor of aldosterone by competitive binding to its cognate receptor in the tissue of the kidneys. So really, I have no idea, and this is truthful, I have no idea what cognate receptor actually means. I know about receptors, have no idea what that word means. But again, I'm not going to let that panic me, because this is something that ACER will try to do. They're always throwing you stuff that you don't actually know, right? But the reasoning behind it is stuff that you do know. So understanding how receptors work, understanding what competitive inhibition is going to be helpful. Knowing what a cognate receptor is going to be completely irrelevant though, right? Otherwise, they will define what that means. Then studies into aldosterone synthase inhibitors, so ASI, so we've got a second definition now, are also being undertaken for their potential therapeutic benefits to some patients with aldosterone abnormalities. Cool, so I've got those 2 bits. We've got MRAs and we've got ASIs. They both seem to be some form of inhibition to this cycle. So I'm just going to know, okay, medications and treatments are coming in there. How many more or fewer chiral centers does aldosterone have than corticosterone? So with this one, this is just a straight up chemistry question. They always have a chiral centers question in there, right? So this one, though, I've decided to make it about how many more or fewer, just to see if people are reading the question closely. So if we look through it, what I would do, you can count the number of chiral centers in each of them and then compare them and look at which one has more or less. And we're looking for aldosterone, so does it have more or does it have less? What's slightly quicker, though, is you can just compare these 2 compounds and then just look for what the change is. Because with an organic pathway, there's always just one small part of the compound changing, right? whether something's being rearranged or something's being added or something's being deleted. So if we look at this, the first thing that I've done is flipped the molecule so that we've got all these stalks coming towards us on the corticosterone, but then away from us in aldosterone. It's really just the same molecule flipped around the other way, right? So anything pointing out of the page would then be pointing into the page. So it tricks you into thinking there's more that's changing, but it's the exact same compound. If we map everything around, we can see it's a mirror image. So these two here are equivalent. It's just been flipped. So we can kind of trace it back and we can go, okay, check this ring here. Yep, it's got the double bond. It's got the double bonded oxygen. Then we go, yep, we've got a methyl group there. Yep, there's our methyl group going back into the page. Then this one here, that one's going into the page there. This is coming out, so that's all the same. And you can track it all the way through. You can see there's your hydroxyl group. Keeps going. There's nothing changing until we get down to this spot here, which was a methyl group. And suddenly there's not a methyl group, there's a CH, and then it goes to a double bonded oxygen. So that is where the change has happened. So in terms of counting the chiral carbons, we don't have to worry about anything across here because all that is equivalent, right? So really, the only difference is, did we have a chiral carbon here, and then did it become chiral or achiral here, right? So beforehand, we had CH3, and I might just zoom that in a little bit so that we can see that a bit more closely. If you think about CH3, if that's the only carbon that's actually changing, that would have been 1, 2, 3. This would have been back to all the rest of it. H, H, H. This is not chiral because it doesn't have 4 different constituents or 4 different attachments to it, which is what a chiral carbon actually needs. So this was achiral. So the only option is that it either stays the same or that it gains a chiral carbon, right? But over here, this is a double bonded oxygen. You can't have a chiral carbon with double bonds attached to it. It has to all be single bonds with 4 different attachments. This would have the R group, then it would have a H, and then it would have an O. So it doesn't even make up 4 attachments, let alone 4 unique attachments. So therefore, this also does not have a chiral center at that point. So without even counting the number of chiral carbons, I know that there was obviously no change in the chiral number, and so therefore the answer should be C, like that. So then moving along, the next one, question 2, how many chiral centers are there in corticosterone? So realistically, they probably wouldn't give you 2 chiral center questions in a row, let alone even in the entire exam, because once you've gotten one, you're probably going to get the other one right as well, and they're trying to really separate the crowd. But I've done this just as more practice, as an alternative, just to show how the questions can be adapted in different ways. How many chiral centers are there in corticosterone? So I'll get rid of all of my scribbling here so we can count it. And with chiral centers, we're just looking for all the carbons that are sp3 hybridized. If we want to be fancy about it, really it just means it has 4 different attachments. So I'm just going to kind of scan left to right and move my way around the rings. So here, this would have a H and a H. It's just skeletal structure. We don't see the hydrogens attached. So that does not have 4 unique things. This one here is a double bond, so that one's out. This one here has this group this way, this group this way, and this group this way. And because this ring is not symmetrical down that bond there, it means that this bond and this bond are actually considered to be different attachments. And then don't forget, it would also have a H just not shown. So that would be 4 unique ones. So that there would be our first chiral center. If we go around this pentagonal ring here, anything that just has single bonds would have a CH2, CH2. So anything with 2 hydrogens doesn't have a 4 unique bonds. So these are all out. That's no good, that's no good. This one here, again, it's not symmetrical through this point here. So we can know that it's got an attachment here, a different attachment this way, different attachment that way, and then a hydrogen. And so therefore this is our second chiral center. So we've got 2 now. All the way around, we go to this carbon here. And again, we can see it's got 4 different R groups attached. So that would be our third. This has got a CH2. This here would have an OH and then different bonds each way. Again, not actually symmetrical, because going this way, it's got this kind of group, and then going this way, it's got this group, which are different visually, right? So therefore, with a hydrogen, that would have 4 different attachments. So that would be our 4th chiral center. This one here, same thing. I think this is getting a bit repetitive now, so I think we get the picture. 1, 2, 3, so we got the 5th one. And then this one over here would also be different as well. So this would be the 6th. And then finally, we have over here, this would be the 7th. And then this one here has a double bond, so it's not possible. This has just single bonds with CH2, so they're not possible here or here. We already ruled out this carbon. And then that one's got a double bond. So we have all up 7 chiral centers in that compound. So we can come across over to here, we're very zoomed in, and then the answer is D, like that. Question 3, a patient requiring the use of a MRA may be experiencing which of the following? So if we go back, because truthfully I would have forgotten at this point exactly what MRA was, and I'd want to confirm it. MRA was an antagonist to any receptor of a mineralocorticosteroid, and aldosterone is classed as one of those. So really it's a type of aldosterone inhibitor. And what does it do? It inhibits aldosterone by binding to its receptor. So effectively it's blocking the active site of its receptor. So then which of the following would be experienced by a patient that requires the use of one of these inhibitors? So really then what I'd do is try to create like a pathway. So it just says aldosterone, like this. We then have the MRA blocks the aldosterone. I like to just do arrows with a cross on it like that. And I go, well, what was the effect of aldosterone here? So aldosterone was used to increase sodium reabsorption into the kidneys. So normally this would cause increased sodium reabsorption, so therefore in the blood, I might just put sodium blood. And then this is where a bit of the biology comes in, right? I would know as well, what would that do? It would drag water in with it under osmosis, right? On an osmotic gradient. And I can kind of get a hint at that because it also said that it regulates blood pressure. So that's my kind of clue that yes, my line of thinking of using some background knowledge and just scientific principles, not technical knowledge of aldosterone, could be on the right path. So that would mean then that would be increased water retention and therefore increased blood pressure along with it, and increased blood volume as well. So these are all my notes. So now I've got it all summarized. So now I know if MRA is trying to block aldosterone, it's trying to block all of this. It means we don't want high water retention. It means we don't want high blood pressure, right? We want to keep it low. So what would they be requiring? Low blood volume and low blood pressure sounds kind of right. But notice this is a trick in the question that I've put here in the way that I've worded it. It's not what is the effect of the MRA, it's what would that patient what would the patient that requires it be experiencing, right? So if they have something going wrong, the solution is to not raise their blood pressure or their blood volume, right? So that would mean that they would not have low blood pressure, low blood volume, because we'd want to raise that, right? So that can't be it. The next one then would be ineffective aldosterone synthase. So aldosterone synthase was over here. I'll just put AS, and that came from the corticosterone, right? If that was ineffective, then that would mean that you wouldn't be getting aldosterone like that. And so blocking aldosterone is completely useless because you're not actually making it then, right? So that doesn't make any sense. So the next one then says concentrated urine. So my thinking here would just be, well, this is obviously to do with salt, right? Salt and water balance. So we saw before that the person who requires MRA would actually have high blood volume and high blood pressure. That would mean they're already retaining a lot of water, which would mean there's very little water getting through to the urine, and therefore there'd be low water, high concentration of solute in the urine. So that one's looking pretty good. And then lastly, kidney failure. So kidney failure, it said here that it was something that was produced, the adrenals here, and linked with kidney function. There's no real direct links as to why this would be true. And so that one's not really got any evidence going for it. And so I'd leave that one out. This one had some evidence going for it. So I'm going to go with C. Again, no, you don't actually need to know about the technicalities of water balance or anything like that. If you notice, I've reasoned that with only the information provided and the concept of low water means high concentration, which is more like a general scientific principle rather than a technical one. And I've also confirmed my answer by doing process of elimination. So I'm not relying entirely on previous knowledge. And then question 4, the reaction catalyzed by aldosterone synthase could be classified as. So again, a lot of jargon in there to try to throw you off, but really we're just talking about the reaction that was given. So where did aldosterone synthase come in? It's all tongue twisters, is here. what would that type of reaction be? So we've got different types of organic or chemical reactions. So first of all, a polymerization reaction already doesn't seem right, because that's where you're gluing two alkyl groups or two organic compounds together and then forming a polymer, right? So poly meaning many, mer meaning parts or units, and so like many parts, many units. That's not really what's happening here. We're just altering an existing structure. So that one doesn't look very good. An organic oxidation reaction, if you remember from the organic pathways one, I think that was the second chemical or chemistry crash course. I think it was the 4th crash course video altogether in the series. I go through organic oxidation, and there's a trick to it. Oxidation is the loss of hydrogen and or the gain of oxygen. So if we look at what happened, remember we isolated and we said it was this methyl group here turning into a double bonded oxygen. So what really happened there, or didn't turn into it, we attached a double bonded oxygen. So we had CH3, and now we're going to CH double bonded oxygen. So what's happened is we've lost 2 hydrogens, which is good news for oxidation, and we've gained an oxygen. So we've got both a loss of hydrogen and a gain of oxygen. They can also happen in isolation, but there we've got evidence of a form of oxidation by definition. Then it says a hydrolysis reaction. That's where you add water to split things apart. It's the opposite of polymerization. That's not happening. We're not splitting anything apart. And then an organic isomerism. So remember that isomers are the same, they've got the same ingredients, the same number of each element in its atomic form glued together, but in different structures or different arrangements. And here we're quite literally removing some atoms and adding some atoms. So it cannot be an isomer of itself. And so therefore it's not isomerism of any kind. So again, process of elimination and some, supporting evidence, we get the answer is B. There we go. So hopefully that's all worked out well for you on that one. We'll move along to Unit 2. So it's effectively a more detailed look at the same system, but bringing in more of the biology and the kind of cell signaling pathways of it. So the renin-angiotensin aldosterone system, or RAS, is the hormonal pathway that regulates blood pressure, blood volume, and electrolyte concentration in the blood. It also has impacts on the urine volume and urine concentration. So it's written in a way as if like the previous unit didn't actually happen. These are all just designed to be kind of randomized. Any one could pop up in a test kind of thing. The system is summarized in figure 1 below, blah, blah, blah. Again, I might scan over it just to get a sense of which direction I'm reading it, where are the arrows going, if there's anything that I'm not familiar with that I should be aware of, but otherwise I would skip over that. And then stimulatory responses are denoted as plus signs, while inhibitory responses are denoted with negative signs. So angiotensin converting enzyme, or ACE inhibitors, are a class of drug that is used to inhibit the enzyme responsible, hey, there's another typo, for converting angiotensin 1 to angiotensin 2. And I can see that over here. Here's ACE, that is stimulating the conversion. But then we've got ACE inhibitors, so watch out for that, are a class of drug that inhibit that enzyme, right? So hypertension is a condition in which a patient has the higher than normal blood pressure. Hypotension, a condition where they have lower than normal. Another little typo there because whenever I type, I just become dyslexic at that point. So these two here, again, you may already be familiar with these from some physiology studies and that kind of thing in second year, maybe even in first year of your course. But like I said, they don't necessarily expect you to know technical stuff. They often define a lot of jargon for people, particularly that are coming from non-science backgrounds. So you don't have to panic too much about memory. So get rid of that. So question 1, patients with kidney failure are likely to experience which of the following symptoms if unmedicated? Okay. So first of all, if the kidneys aren't working, I'm going to find where the kidneys come in. And you can see here are the kidneys here, here, and here. So now we're going to go with they are not working. Although technically I've circled this one, tricked myself there. That's the adrenal gland, not the kidneys. So I'm going to leave that one off. Just these two here, they're going to be kind of contributing or not contributing if there's a failure. So if there was kidney failure, then it would mean that you wouldn't have renin production, which means therefore renin looks to be stimulating the conversion of angiotensinogen into angiotensin 1, which is kind of kicking off the whole process. So we're blocking it right at the start. If we have no kidney function, we have no renin, and therefore we have none of anything downstream of it at that point, because there's no negative loops in there or no negative feedback. And so then over here, the kidneys are also contributing ACE as well. And so given that that's not going to be happening, it would mean that we would be also switching off this path, but that doesn't change too much because it was already being switched off a step before. So in that case, if we don't have this happening, and the goal of aldosterone, which is one of the end results here, was to raise BP, then that would mean that we would not have a raising of BP possible because the kidneys aren't working to achieve this. So hypertension, high blood pressure is not actually possible in this case, ignoring all other effects, right? Arterial constriction, so it says here arterial vasoconstriction also occurs, but if we've blocked the pathway up to that point, we're blocking that, which means that's not possible as well. The next one then is overactive pituitary gland. So then overactive pituitary gland, here it is over here, that would be getting blocked as well, so that's not possible. And then finally, we've got dilute urine. So where would that come in? That would again be into the electrolyte balance and the water balance. The goal of this pathway was to pull the water back out of the urine, back into the blood. And so if we're not able to do that, then the water stays in the urine and therefore we dilute the urine, right? And so that would be the most appropriate. Again, you could overthink this and look at things like it did say electrolyte reabsorption. So you could argue that, well, you're not pulling back electrolytes as well from the urine, and so therefore there'd be more electrolyte in the urine, and therefore it would be concentrating at the same time, so it's somewhat ambiguous. But we go with the process of elimination. The other three are absolutely false, whereas there's a possibility for D to be true, and so we go with that. So then question 2, dehydration is likely to be which of the following? So again, let's just get rid of all this. So dehydration is likely to be the cause of RAS-related kidney failure. Let's have a look here. So RAS, first of all, is just the whole system. So this whole thing is RAS. Kidney failure. So it's pretty unlikely because there was no talk of kidney failure in the actual question. That seems to be outside of the stem itself. There was mention of kidney failure in the previous question, almost like a word association trick, but there's nothing that suggests kidney failure is occurring. So that one already doesn't look very good. The cause, so dehydration is likely to be the cause of stimulation of renin secretion. So we look for renin, it gets secreted by the kidney, but the kidney gets inhibited, this production gets inhibited by the effects of aldosterone here, or the whole pathway. So raising BP and blood volume inhibits renin production. And then also it says here a decrease in renal perfusion or juxtaglomerular apparatus promotes it. We don't even really need that there, but we can connect that here. This one says perfusion of that increases, so this is the opposite. So high blood pressure, high blood volume, this would mean we can connect this to low blood pressure, low blood volume as the potential stimulus to renin production. Dehydration, though, is when you have low blood volume, right? So if you've got low blood volume, then that would be here, that would be the stimulation of renin. So in this case, the cause of stimulation of renin secretion would make probably the most sense in this case, right? And then moving along, the cause of a decrease in tubular reabsorption of potassium. So if you have dehydration, then this here, the cause of a decrease in, if we notice tubular reabsorption goes up when this pathway is activated, which is activated by dehydration or low blood volume. And so therefore this one says decrease, which is the wrong way around. And lastly, it says the result of angiotensin converting enzyme stimulation. So ACE is over here. And then if you have stimulation of ACE, that means you have stimulation of this, which would lead to an increase in blood volume and blood pressure. But dehydration would actually be the cause of that, not the outcome, right? It would actually be rehydration or reabsorption of water or retention to fix that problem. So it's actually the word result. It's got the cause and effect relationship the wrong way around. You can see that dehydration is starting further back before that. Cool. So it would be that the dehydration would be the cause of ACE, effectively, ACE in stimulation. So the only one that had anything going for it again is B. So you can see these ones, a lot of process of elimination when you've got a lot of qualitative analysis. Then question 3, we have a particular medication, drug X, has an inhibitory effect on 2 elements of the RAS. If drug X is administered to a patient also on ACE inhibitors to treat high blood pressure, and they find that their blood pressure in fact rises, which 2 tissues or compounds may be possible targets of drug X? So this is a really tricky one. And truthfully, when I was writing this, I had to make sure that I wrote everything down and kind of went through all the scenarios just to make sure, because it's one of those ones where there's lots of different permutations and combos. So what I would do in that case then is no point trying to hack it and kind of get straight to the answer. I'm just going to test each option and see which one works. And I'm also going to make sure that I rule out the others because I'd be pretty nervous about this one. So first of all, they give us a bunch of information. It says drug X inhibits 2 elements of the RAS. It's also going to be given to a patient who is already on ACE inhibitors. So we're already blocking this pathway to begin with, which means we're blocking this pathway effectively, and then everything downstream of it. The next thing then it says is their blood pressure now is going to rise when they give them drug X because of this double inhibition. Which 2 tissues? So if we go into that, right, they were already on ACE inhibitors because their blood pressure was high. Then you block the process that raises BP. This whole process raises BP. So if you block it, you block the raising of BP to keep the blood pressure lower, right, or constant. So if we look at kidney and ACE inhibitor blocking, I'll do this in another color here. I might just lock the page for a moment. There we go. So if we block the kidney or inhibit the kidney, then it means we can't get renin production, which means we block this, right? Which effectively has the exact same effect as the ACE inhibitor because you're just blocking it earlier or downstream of it. But we're also blocking the ACE inhibitor. So if we do that, if we block this, we double block the inhibition and we actually open that pathway back up, which means now this can go like that. The problem is that we've actually blocked it back here at the renin. So even though we've opened up this pathway, the renin's not happening, which means we're not converting into angiotensin 1 in order to use the ACE to convert it to angiotensin 2 and then cause a rise in blood pressure. So that wouldn't actually explain the rise in blood pressure. So that doesn't look very good there. So if we block ACE, they're already having ACE blocked by the ACE inhibitor, right? So really that's going to have no actual measurable effect really. But if we block the angiotensin 2, then what that means is we're blocking this pathway here, which is already being blocked as well from here. We've already got the ACE inhibitor, and so we've already switched this path off. So even if we switch this path off, it won't make a difference. So we just have more inhibition of the raising of BP. And so, so with the liver, we're blocking it all the way back here. If we block the liver, then we're blocking the pathway further upstream. And so the ACE inhibitor is already blocking it further downstream. So blocking it further upstream is not going to do anything. You're not going to notice any effects. And then blocking the kidney altogether, not just the inhibition of the kidney, but the entire kidney, then that'll mean that you'll have no renin production, which will mean that you block it here as well. But again, we're already blocking it at this phase with the ACE inhibitor. So that would not have any measurable effects. So this is then going to be out. And then finally, we have ACE inhibitor and adrenal gland. So this is a tricky one. So if we block the ACE inhibitor, we reopen the pathway again, which means we get angiotensin 2, which means we get everything that stems off of that. The adrenal gland is responsible for aldosterone secretion, right? You can see here. So we would be blocking this, which means we would not get much of the water retention. But remember that we do have angiotensin 2, and that can also stimulate tubular reabsorption and therefore water retention and a raise in BP. And we can also get vasoconstriction from the arterioles, and then that would also raise the blood pressure to be squeezing in on the blood. And these things would cause a raise in BP. So if we're blocking those two, ACE inhibitors and the adrenal gland, we actually can open up the pathway to raise the blood pressure again. Cool. So the answer then will be D. I'll leave those scribblings on for the moment. So then question 4, the last one, consider the following statements. We've got blah, blah, blah. Again, never read these, just go straight to what you're looking for, true or false, and then check each one as you go and tick them. So arteriolar constriction occurs when aldosterone secretion is stimulated. So if we have a look at that, I'll get rid of all this stuff again. When the arterioles constrict, that occurs here. It says, does that occur when aldosterone secretion is stimulated, right? So aldosterone is over here, which is occurring at the same time because they're all being promoted by angiotensin 2. So it's a trick because no arteriolar constriction is not because of aldosterone. That goes off and causes water retention changes, but it just says when, so at the same time. So if you've got aldosterone secretion, then it means you've got angiotensin present. And therefore, if you've got angiotensin present, then you're also getting arteriolar constriction. So that would be true. The next one then says ACE could be used to treat anemia or low iron levels. If we look at this here, there's nothing mentioning iron. Yes, iron is a mineral or a metal in the blood, but it is not considered one of our key electrolytes that are being mentioned here in terms of water balance. And so therefore, that one would be false. Again, you may know something that I don't know about iron relating to water retention, but given there's no information that would give us that in the question, it would be irrelevant information. And then a high sodium diet may increase aldosterone secretion. So again, we'll get rid of all of this. So if we have high sodium, right, high sodium would mean that we would have lots of sodium in the blood. If we have high sodium in the blood, then we have a lot of water in the blood because it's going to osmotically drag water in, right? If we do that, then we're going to have high blood pressure, and then this will create a cycle. So when we have high blood pressure, it's equivalent to having a whole lot of aldosterone being released. And what does that do? That then has a negative feedback loop on the kidney to prevent renin production, to then decrease angiotensin 1, to decrease angiotensin 2, to decrease the stimulation of the adrenal cortex, and therefore decrease aldosterone secretion. So this says a high sodium diet may increase aldosterone. No. High sodium would be equivalent in its impact on the system as if you had high aldosterone, but it'll actually have a negative feedback loop onto it and it'll actually decrease it. So therefore, the only one that was correct is statement 1. And see, we haven't even looked at the answers here. Now you know it's got to be B, like that. There we go. Cool. So hopefully that was helpful to just go through something in a little bit more detail. Again, you can see that one's a bit more of a balance towards kind of technical analysis of the information. It's not requiring you to come in with a huge amount of like expert knowledge on the topic. In fact, that would probably throw you off a lot more. So if you're from a non-science background, it's a little bit more accessible. Let me know how you go with them as well, how you're finding them in terms of difficulty, if you think that the ratings that I'm giving them are fair, or if you're finding them a little bit tricky or easier than the way that I'm rating them. Like I said, these I've put as an easy rating. So yeah, let me know how that fares. Otherwise, hopefully this was helpful. Again, I do these partly so that people have lots of practice with freely available questions that are, again, hopefully reflective of the ACER material, so you're not having to pay for anything. But because I know I wish when I was studying for mine, I wish that something like this was available, so that's really what's driving me to do this. The other thing as well is a lot of people want to see strategies, like obviously looking at like the way that I had approached my own sitting. People wanted to see how I approach section 3 questions, how I might read them and take insights from them. I'm trying not to, I guess, overanalyze them, because really a lot of it might just be things that I don't really think about. So I try to just run through what my thoughts are as I read it, as if I were to be sitting it for the first time. And hopefully you're taking a lot from that. If you do want more kind of analysis / commentary, let me know, but I try not to have too much of that in these videos, or else it kind of distracts from the worked solution as well. Because I know a lot of people are probably watching these just to kind of understand how the question works if you were getting stuck with it. So I'm trying to balance those two elements, which sometimes can be a little bit tricky. But again, feedback is always appreciated, so let me know. Otherwise, I'll leave that one there because this one's gone a little bit longer than I hoped that it would go. So I will see you in the next one.